So just to review a little bit of where we were last time, we were talking about some fundamental patterns that show up in carbonyl chemistry, and today we'll see a little bit about how they apply to mechanisms. And we discovered that because of the bonding nature of the carbonyl, with its delta plus on the carbon, delta minus on the oxygen, that when a carbonyl is present in the beginning of a mechanism step, there are three fundamental common things that it's going to do. There are other things that it can do, but these are the common ones you're going to see, and this is very much like the idea of carbocation phase. The carbonyl can accept a nucleophile of the carbon because of the delta plus of the carbon. So there's the nucleophilic attack. The carbon-oxygen pi bond has to go away so that we don't have a pentavalent carbon. That leads to a structure in which the carbon is now sp3 tetrahedral, so we call this the tetrahedral adduct. And we can also have the carbonyl accept an electrophile at the oxygen. Most of the time that electrophile is a proton, although other things can show up there occasionally. Protonation requires strong acid, aqueous H2SO4, H2SO4 itself, that kind of thing, strong acid. And there was a question that we answered last time about position of the protonation. In other words, we could use the lone pairs, which would lead us to this oxonium ion structure, or we could use the pi electrons, which would lead us to this carbocation structure. And we discussed which one of these is preferential, and in fact it's a moot point because these two structures that are formed from these curved arrows are resonance contributors of the same structure. In other words, whether you use the lone pairs or the pi bond, it leads you to the same structure. In here we'll use the lone pairs a lot because it looks more natural, because it leads more directly to the more significant contributor, but we can use either one. The third possibility, the third fate, is to remove the proton next door to the carbonyl to give an anion which has resonance stabilization, lone pair next to the carbonyl. This resonance contributor to the anion taken together are called the enolate, and we will talk more about enolates later. We're going to talk mostly about reactions at the carbonyl group for the moment, so this one not so important for us. Now, what we can do then is to take those carbonyl fates and to expand them into generic carbonyl mechanisms, to make some predictions as to what might happen overall in a carbonyl reaction mechanism. Well, start with nucleophilic attack on the carbonyl. That gives us the tetrahedral adduct. Now, in this particular case, the tetrahedral adduct has a negative charge. It won't always have a negative charge. If the oxygen is protonated to begin with, then the tetrahedral adduct will be neutral, or at least the oxygen will be neutral. And now this tetrahedral adduct, when it has a negative charge on oxygen, and even when it doesn't, but mostly in the case where it has the negative charge, wants to get rid of that negative charge. And we discussed there are two ways to do that. It can either eject a leaving group, which would return the carbonyl, or it can pick up a proton on the oxygen, which would give us an OH. Now, between the two of those, generally speaking, intramolecular processes that happen within the molecule are often, not always, but often enough to be a good guess to begin with, intramolecular processes are faster than intermolecular processes. So the tetrahedral intermediate will try to do the intramolecular process, that's eject the leaving group first. If there is a reasonable leaving group, then that will restore the carbonyl, and the net effect can be replacement of the whatever was attached to the carbonyl X with whatever the incoming nucleophile was. So the net effect in that is substitution at the carbonyl. We call it nucleophilic carbonyl substitution. But if there's no reasonable leaving group, then we can put the proton on the oxygen, and the net effect is addition. There's the nucleophile, there's what used to be the carbonyl, there's a hydrogen. So fundamentally, carbonyl reactions are going to be either substitution at the carbon of the carbonyl or addition. That's it. Now, we're going to talk about a lot of different kinds of carbonyl reactions in here, because there's a whole bunch of different carbonyl-containing functional groups. There are many, 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 many kinds of nucleophiles, and as we go through this, you'll see these reactions can occur under neutral conditions or base catalysis or acid catalysis. So take all the functional groups times all the nucleophiles times the possibility for conditions, and there's a lot of them. So if you're a memorizer at this point, you should be running from the room screaming. But if you are a person who has learned to think about organic reactions in terms of patterns, you should be going, hey, this looks like it's going to be easy. Now, initially, it's a little bit difficult until you see the patterns, but once you see the patterns, and we're going to emphasize them as we talk about reactions, once you see the patterns, it makes your life easier. So really think about the patterns will be very useful. Now, another common question that comes up at this point is about why can't I just do, if this is a substitution pathway, why can't I just do everything at the same time? Why can't I just have the nucleophile replace the leaving group directly? Why do I have to do this addition-elimination mechanism? And that's because, well, SN2s just don't occur at sp2 or sp carbons. It's usually a combination of steric hindrance of getting nucleophile in plus the nature of the orbitals that are involved. So as tempting as this is, we can't do it. Now, the last thing we talked about last time, excuse me, was some examples in terms of the mechanisms. And if we take a ketone and react it with water, we can do an addition reaction. And because there is no leaving group in the case of a ketone, this has to be addition, not substitution. And you can tell that because we started with a carbonyl and ended up with no carbonyl. On the other hand, if we have an acid chloride where there's a leaving group chloride, then the nucleophile can replace the chloride. Again, it's got to go through this addition-substitution mechanism. But the nucleophile can replace the chloride, and the net effect here is a carboxylic acid. But, important pattern to notice, we start with a carbonyl, we end up with a carbonyl. That's substitution. All right, so that's where we were last time. Now, what we're going to do today is to start talking about relative rates of these reactions. This is important for two reasons, multiple reasons, two reasons though. Number one, what we're going to talk about here will really get us thinking about how these reactions work. So yes, we're talking about rate, but we're also going to be talking about mechanism and factors that influence that. Number two, although a lot of textbooks don't emphasize this rate issue a lot, it's really important in biology. A lot of reactions that occur in organisms have carbonyls in them. And the relative rate of those reactions is pretty important to have the organism maintain its, well, life functions. If the carbonyl reactions were all too fast or all too slow, it would be a problem. We're going to see a biologically important example of comparative rates when we talk about substitution reactions. Let's start by talking about addition reactions. So that's going to involve aldehydes and ketones. We're going to do addition reactions first because it's mechanistically a little bit simpler. Let us imagine for our comparison we wanted to compare the rate of addition of methoxide to an aldehyde versus methoxide to a ketone. Now, the nucleophile is the same. That's not what the difference is. The difference here is the aldehyde versus the ketone, and that's what we need to focus on when it comes to comparing the rate. But also, if we're comparing rate, we need to understand mechanism because we have to see whether or not there is, if there are multiple steps in the mechanism, we've got to figure out the one that's rate determining. So let's look at our generic mechanism. It's not going to matter whether it's an aldehyde or a ketone. The generic mechanism is this. Here's our carbonyl, nucleophilic attack on the carbonyl to give the tetrahedral adduct. And now it's a tetrahedral adduct with a negative charge. So there's two things it wants to do, but one of them it tries to do first. Anybody remember? Tetrahedral adduct, negative charge on the oxygen. The first thing it tries to do is? Maybe if we go back to here. Tetrahedral adduct has two choices, eject a leaving group or accept a proton. Which does it try to do first? Eject a leaving group because that's the intramolecular. Remember, this is my first wife hitting me and this is the guy in the pickup truck hitting me. Remember that? Now you remember. But generally the reaction within the molecule happens faster. So we consider that first. It doesn't mean it always happens faster. It's just a good place to start. So here we have a tetrahedral intermediate with a negative charge. Does it have a leaving group that can eject to restore the carbonyl? Now, up to this point, we would have said no, because OCH3 minus, not a leaving group. Well, finally, after 7.5 weeks, wherever we are in this course, now we have the circumstance in which RO minus can leave. When we have a negative charge on the oxygen, it can kick out another thing with another negatively charged oxygen. But it's got to be a negatively charged tetrahedral intermediate. If this was neutral, if this was OH, then that OH couldn't kick out the OCH3. And we talked about this last time. We justified doing this in two ways. Number one, in the transition state for this leaving group ejection, the negative charge is shared by two highly electronegative atoms. So that helps. Number two, there's lots of lone pairs in the vicinity of each other. So that also helps things to leave. In the same way it makes an oxygen-oxygen bond weak when we talked about free radicals, same thing here, lots of lone pair repulsion. So if we kick out the OCH3-, well, that goes back to where we came from. So it's not important for this particular case, but I'm mentioning it because we're going to see a lot of RO- leaving groups in carbonyl chemistry. So if there's no leaving group that we can eject to move the reaction forward, then we try protonation. In fact, we had a protic solvent, methanol in both these cases. So we put the proton on, get the tetrahedral intermediate. Or excuse me, get the addition product. Overall, we have a two-step mechanism. Nucleophilic attack, proton transfer. Now, if we're going to talk about rate, since it is a multi-step mechanism, we need to figure out which one of those steps, if we can, figure out which one of those steps is rate determining. Now, we already know the answer to this because we've used this principle before, but in the event you don't remember, let me remind you. Nucleophilic attack, proton transfer. Anybody remember we had kind of a general rule about that? Proton transfer is, right, proton transfers are generally not rate determining. They're generally pretty fast. So when we focus on the rate of this reaction, for this case, this is the step we're going to look at, the nucleophilic attack on the carbonyl. Now, so we're comparing methoxide attacking an aldehyde versus methoxide attacking a ketone. We're making a comparison, so we want to look for differences. In both cases, it's the same nucleophile, so we don't have to worry about the strength of the nucleophile. If there were different nucleophiles, we would worry about the strength of the nucleophile in the same way that we always think about the strength of the nucleophile. Remember, we learned all about nucleophiles in SN2. Exactly the same arguments would apply. But this is the step we want to focus on. So what I would like to do then is to compare some factors. Now, there's really two factors to think about. Number one, steric effects. A ketone, here's our ketone, acetone, the carbonyl is flanked by two methyl groups. In the aldehyde case, the carbonyl is flanked by one methyl and one hydrogen. What's the difference? Methyl versus hydrogen. Now, methyl groups, of course, are larger than hydrogen atoms because methyls are methyl groups and hydrogen is one atom. And there aren't too many things that are smaller than a hydrogen. So methyl is bigger than a hydrogen. What do we conclude then about steric hindrance? Which one of those two carbonyl carbons, aldehyde or ketone, is more sterically hindered? Ketone, right? This is like you're doing an SN2 reaction on a primary carbon or a secondary carbon. More alkyl groups makes more hindrance. So because the ketone is more sterically hindered, we can conclude that this, just based on this factor alone, the ketone addition, nucleophilic attack on the ketone would be slower than nucleophilic attack on the carbonyl. Now that's based just on the steric hindrance, and we have to look at other factors because other factors may not necessarily be synergistic. Well, the carbonyl is the electrophile here. The methoxide is the nucleophile. The carbonyl is the electrophile. So let's ask how electrophilic is that carbonyl? Again, what's the difference between those two carbonyls? Methyl versus hydrogen. Now we're thinking about the carbonyl as an electrophile because it is electron deficient, delta plus on the carbon. The bigger that delta plus is, the more powerful an electrophile it is, the more inclined it is to accept a nucleophile. So the question we need to ask here is, which has the bigger delta plus on its carbonyl carbon? An aldehyde or a ketone? Remember the difference, hydrogen versus methyl. How does a hydrogen versus a methyl influence the delta plus on the carbonyl carbon? Let's be even more generic about it. Imagine you have a carbon that's electron deficient. You put a methyl group next door. Does that reduce or magnify the delta plus or the electron deficiency on that carbon? It reduces it because methyls are electron donors. Methyls stabilize carbocations. Methyls, in terms of electrophilic aromatic substitution, are they orthopara or metadirectors? They're orthopara directors. Why? Because they stabilize carbocations. Here we're talking about a delta plus on a carbon. It's not a full-blown positive charge. It's a delta plus, but it's still electron deficiency. So what does a methyl group do? Well, it's an electron donor. So it's going to decrease the magnitude of that delta plus relative to a hydrogen. I've written here hydrogen is electroneutral, and that's my way of saying it's not donating, it's not withdrawing, it's just kind of watching. It's not participating in a meaningful way. So here, in the ketone case, the delta plus on the carbonyl carbon is smaller than the aldehyde case because the ketone case has 2 electron-donating groups flanking the carbonyl carbon, where the aldehyde only has 1. So in terms of rate, then, which, based on the delta plus on the carbonyl carbon, which of these two should have a faster nucleophilic attack? The ketone with a smaller delta plus, or the aldehyde with the larger delta plus? Which is slower? The ketone, because the delta plus is smaller. So these mirror the steric effects conclusions as well. So in this case, the two effects are synergistic. We're saying that overall, ketone is slower to accept the aldehyde because the ketone not only is more sterically hindered, but the ketone has a smaller delta plus on its carbonyl carbon due to the electron donating effects of that extra alkyl group. So there's our summary. Slower, faster. The factors are synergistic. It's good that they work together. Now, here we've made the analysis for aldehydes versus ketones. For one aldehyde, acid aldehyde, versus one ketone, acetone. If you look at aldehydes and ketones as a whole, the factors are going to work the same. Regardless of what the nucleophile is, regardless of what the aldehyde or the ketone is, these factors are going to be pretty much the same. Most ketones are more sterically hindered than similar aldehydes. Most ketones have a smaller delta plus because they have more electron donating groups than similar aldehydes. So in general, we can expand that idea to all addition reactions of aldehydes and ketones and conclude, in general, the rate of addition for aldehydes, is that going to be faster, bigger, or less than ketones? Bigger. Aldehydes are faster. So again, based upon steric hindrance and the magnitude of the charge on the carbon. Now, let's take that idea and expand it to substitution reactions. There are similarities between additions and substitutions, but generally substitution mechanisms are longer. There's a few more steps. There's more stuff to consider. Now, for our comparison purposes here, I said I was going to give you a biological example. Let me give you a biological example of some substitution reactions. Let's start by talking about the reaction of an amide with water. Important because, well, proteins are held together with amides, and there's an awful lot of water running around in your body. And we know, just from common sense, that amides are relatively resistant to substitution with water. In this case, the substitution would give a carboxylic acid plus an amine. Why do we know that? Well, because we have proteins. We're not just an aqueous sack of 20 different standard amino acids running around. I mean, imagine you went down to Carl's for lunch. Not that there's much protein in what Carl's serves you, but imagine you went to Carl's for lunch and you ordered a hamburger, which, by the way, has got a lot of water in it. Right? What is it? 1/4 pound pre-cooked weight. And what percentage of that is ice before they cook it? But that's water, right? So when they serve you the hamburger, it still has protein in it. It's not just, oh, by the way, here's your 2 buns with aqueous amino acids between them. No, amides resist substitution with water. Now, what about, let's compare that with this guy. Speaking of coughing, that was appropriate there. We're going to talk about this guy, carbonyl with 2 chlorines on the side. It's essentially an acid chloride, but this is, I know it's got 1 chlorine on each side. So it's a little bit different in that way, but it's still an acid chloride. The acid chloride we're going to talk about here is phosgene. Phosgene was one of the first chemical weapons used in World War I. They used chlorine, I think, before phosgene, Cl2. But phosgene it does react with water and other nucleophiles. It particularly kills you because it reacts with free amino groups in your lungs and damages your lungs, and your lungs fill up with liquid and you basically drown, and that takes a couple hours, maybe a day. It's it's a weapon, right? Since when are weapons pleasant? I mean, if you have to kill me, use a hydrogen bomb, okay? I don't want to know it's coming. Don't do phosgene on me. But anyway, so phosgene takes a while to happen, but it happens. It reacts with water relatively slowly. It might take, if you release phosgene in the atmosphere, it might take a few hours before it's hydrolyzed. But it still does a substitution process in which the chlorines are replaced by water, and we now get carboxylic acids. So the point I want to make here is we have 2 substitution reactions at a carbonyl group where water is the nucleophile. Amides are slow. Acid chlorides are fast. What is it that makes for that difference? Let's see if we can figure that out. Now, bear in mind that when we do this, we're trying to draw a general conclusion, so there will be times when we'll say that we can't really count a specific factor that's happening here because we're trying to be general. All right, so again, to determine rate, we need to look at the mechanism. And here's your generic carbonyl substitution mechanism. Nucleophilic attack on the carbonyl gives the tetrahedral intermediate. The tetrahedral intermediate ejects a leaving group. Now, I've left out the proton transfers in this mechanism. If you actually work through the amide plus water and the phosgene plus water, you'll see you have to include proton transfers. But the proton transfers, as we mentioned, are not rate determining. So these are the only two steps in the mechanism which potentially are rate determining. Now, as it turns out, it's not easy, especially if you are making, trying to make broad generalizations. It's not easy to look at this mechanism, this addition-substitution mechanism, and pick one of those two steps and say, this step is clearly always faster than the other one. We can't do that. There's really no obvious rate-determining step here. That doesn't mean we can't make the rate analysis. It simply means we have to think about both what's going on in the nucleophilic attack step as well as the tetrahedral intermediate falling apart step. So we're going to analyze those separately. Let's start with the addition to the carbonyl. And by the way, the addition to the carbonyl here is going to look a lot like the addition to the carbonyl in the aldehyde or ketone case. In both cases, it's a nucleophile attacking a carbonyl to give a tetrahedral intermediate. So let's apply the same things where they apply. Now, one thing that we didn't have in the aldehyde and ketone case was leaving group. Let's talk about that first. Leaving group. In the amide case, the leaving group would be nitrogen with a negative charge, a nitrogen anion. So we call it a nitranion. Like oxyanion is oxygen anion, nitrogen anion is nitranion. So that's the leaving group. What about in the acid chloride case? The leaving group would be Cl minus. All right, let's analyze those in terms of leaving group. Which is a better leaving group? Now, bear in mind we're being generic. We don't know what the R groups are on the nitrogen. So in general, which is going to be a better leaving group? The nitrogen with the negative charge or the chlorine with the negative charge? Well, let's see. We don't know about resonance in the nitrogen because we don't know if the R group is in the nitrogen case. The next thing that matters is atomic radius. Nitrogen is small because it's second row. Chlorine's third row. It's bigger. So that looks like chloride's going to be a better leaving group there. Electronegativity between nitrogen and chlorine. They're the same. They're both 3.0. And then there are inductive effects. And again, because we don't know what the nature of the R group is, we can't make that argument. So it looks like chlorine, Cl minus, is a little better leaving group because of the electronegativity issue. And yeah, that's true. But I'm here to tell you that it's irrelevant. Why is it irrelevant? The fact that chloride is a better leaving group, irrelevant to this step in the mechanism. It's not that it's not rate determining. We don't know that. Let me use a metaphor. If you don't mind me asking, what kind of car do you drive?
I don't drive a car down here.
You don't drive a car. You take a bicycle? Take a bus?
I walk.
You walk. Oh, okay, fine. That's great. So because you walk, you have less carbon emissions than I do because I drive. And I will tell you I drive a kind of old SUV, but it's paid for. Okay? Do you like fruit?
Yes.
Yeah, see? Okay, so because you don't drive a car, what kind of fruit does he like? It's completely irrelevant. Why is the leaving group completely irrelevant to this first step in the mechanism? It's not leaving. The leaving group is not leaving. So the fact that chloride's a better leaving group, so what? Who cares? Irrelevant. That much space in your think book is wasted. Or you can write irrelevant in there, whatever you'd like. So if you paid too much for the think book, then that's the space you paid too much for. Irrelevant. Steric effects. That's something else we talked about with aldehydes and ketones. Well, it's kind of a tough conclusion to make here because, like we said, we don't know what the R groups are attached to the amide. And I'm trying to make a broad conclusion about carbonyl substitution rates. So not only am I trying to draw conclusions about amides and acid chlorides in this particular case, but I'd like to extend it to esters and anhydrides and all of those. Steric effects are all over the map. So in this particular case, kind of hard to say. We could compare in very specific case, but overall, question mark. So we're going to call this question mark because it's going to be very situational. Third factor we have on here, also we talked about in the aldehydes and ketones case, is the magnitude of the positive charge of the delta plus on the carbonyl carbon. In other words, how electrophilic is the carbonyl? Well, let's see. How would that be different? In the amide case, they both have carbonyls, but in the amide case, there's a nitrogen next door, and in the chlorine case, or the acid chloride case, there's a chlorine next door. I'm bringing up those atoms, nitrogen and chlorine, because they're pretty electronegative. And what happens when you have an electronegative atom as your neighbor? Electron withdrawing. And what does that do to positive charges? It amplifies them. That's why electron withdrawing groups are metadirectors. So here we have the nitrogen of the amide taking electron density away, and here we have the chlorine of the acid chloride taking electron density away. In which case is the electron withdrawing effect greater, the amide or the acid chloride effect? Remember, this is an inductive effect. Nitrogen's electronegativity is how much greater or lesser than chlorine's electronegativity? They're the same. So both are equally electron withdrawing. So this, while both of these are amplifying the delta plus on the carbonyl carbon, they are equal. And you might go, well, gosh darn it, this doesn't help. One factor was irrelevant, another one we couldn't tell, and the next one they're equal. But there's something else we haven't considered, because when you think about a carbonyl with an atom next door, say a nitrogen or a chlorine, these atoms next door often have one or more lone pairs. And when there is one or more lone pairs next door to the carbonyl carbon pi bond, lone pair next to pi bond, what should we think about? Resonance. Resonance is an issue. It wasn't in the aldehyde and ketone case. It is here. So now on the top of the next page, we can see how that operates. So in both of these cases, amide and acid chloride, as a matter of fact, in all cases where we have a carbonyl which has a leaving group on it, a carbonyl functional group which is capable of undergoing substitution, virtually every single case, there is an atom with a lone pair. Think about what those functional groups would be. Carboxylic acid, carboxylate, thioester, amide, anhydride, acid chloride. Every single one of those cases has this X atom with a lone pair, and therefore resonance is possible. All right, so here's what the resonance would look like. In the amide case, there's our major resonance, our other resonance contributor. It's not as important as the one we started with, but only because this new contributor creates avoidable formal charges. Other than that, it's a good contributor. Negative charge in the more electronegative atom, same number of covalent bonds, no open octets, so it's a pretty important contributor. Same thing in the acid chloride case. Yes, chlorine can participate in this as well. Now, why should this matter? Let's figure out why resonance matters first before we can judge the difference in the resonance. Resonance matters because nucleophilic attack on the carbonyl destroys that resonance. When the nucleophilic attack converts the carbonyl to the tetrahedral intermediate, the atom with the lone pairs, in this case the nitrogen, or in this case the chlorine, no longer has lone pairs next to the pi bond. Now it's an sp3 carbon that they're next door. So there's no resonance. The nucleophilic attack occurs at the expense of resonance. And as we said before, resonance is like money. How many of you have money? Nobody has money today? Okay, imagine you had money. Anybody? You can't even imagine that you have money, can you? All right, imagine I gave you 20. Imagine I give you $20. I don't have $20 to give you, but imagine I gave you $20. Okay. How would that make you feel? That would make you feel happy. Only $20? You're cheap. Every time I do this metaphor and somebody says, you got to give me 100, then you'll be happy, right? I'm sorry, I don't have 100. I have $20, but I'm not going to give it to you. I'm sorry. Because if I give it to you, I'm not going to get it back. Why? Because money makes you happy. If you don't have money, you would like to get it. What if you had money? Right? Imagine I gave you that 20, you went, woohoo, I have $20, and I said, I'd like it back. Are you going to give it to me?
Am I greedy?
Are you greedy? No, that wasn't the question. You're not supposed to answer a question. You're supposed to answer a metaphor with a metaphor. Normally, if I just walked down the street, if you walked down the street and found $20 on the sidewalk, and then I walked up to you and said, hey, give me $20. Unless I have a gun, are you going to give it to me? No, of course not. Why? Because the money makes you happy. You got the money, you want to keep it. So the thing with money is if you have it, you want to keep it. If you don't have it, you want to get it, right? For how many of you that does not apply? That's what I thought. It's like resonance. If a molecule has resonance, which is a stabilizing feature in the same way that probably money stabilizes you, molecules have resonance, they want to keep it. If they don't have it, they want to get it. So here, the nucleophilic attack on the carbonyl comes at the expense of the resonance stabilization. That means you have to pay an extra energy price to achieve the transition state because resonance is going away. Now, both the amide and the acid chloride lose resonance when the nucleophilic attack occurs. But do they lose the same amount of resonance? In other words, is carbonyl to nitrogen resonance more stabilizing, less stabilizing, equal stabilizing to carbonyl with chlorine resonance? Does anybody remember where we learned this rule? Way back in Chem 14C when we talked about resonance. Remember we talked about the resonance contributor preference rules. We said if the atom next door, especially with carbon, if the atom next door is in a different row of the periodic table than carbon, resonance is less significant. So in other words, carbon to second row element resonance is more significant, provides more stabilization than carbon to third row element. In other words, amide resonance, carbonyl to nitrogen, is more significant, provides more stabilization, and is therefore harder to disrupt than the carbonyl to chlorine resonance. So there is a difference. They both have resonance. It's lost in both cases. But in the amide case, the resonance disruption, it's a greater disruption of stability. It comes at a bigger energy price, so this step is slower. And this step then is faster. And that resonance issue, by the way, is summarized down here. When the X atom is an oxygen, nitrogen and oxygen and even a fluorine, the resonance is significant. So esters, carboxylates, amides, even acid fluorides, that's when there's a fluorine next to the carbonyl, have important resonance. When the X group is chlorine or sulfur, the resonance is there, it's just not as important. And when it's hydrogen or an alkyl group, there's no resonance to be concerned with. So our first step, what do we have overall? If we go back and look at that, we had leaving group irrelevant, steric effects not able to be analyzed, carbonyl delta plus equal, but resonance said that the amide step, the nucleophilic attack on the amide should be slower. And so far that looks good. That's consistent with our observation that amides are slower to hydrolyze than acid chlorides. All right, now let's go to the second step of the mechanism because we're not done. Second step of the mechanism is the one in the tetrahedral addict expels the leaving group. There's really two things to be considered here. One is the nature of the leaving group. And before we spend time analyzing the leaving group, since our fingers were burnt once, so to speak, is leaving group going to matter in this step where the tetrahedral intermediate is ejecting the leaving group? So if you go to this step in the mechanism, right here, this is the step we're doing now, does the nature of the leaving group matter? Yeah, because it's leaving. All right, so now it's worth analyzing. Which is a better leaving group, the nitroanion or the chloride? We've already done this analysis. We decided that chloride is a better leaving group. Remember, if you go back to the beginning of the course when we had our list of leaving groups, remember Cl minus, moderate, nitrogen N minuses only under special circumstances. So the acid chloride has a better leaving group, so and when it comes to decomposition of the tetrahedral intermediate, and we're considering only the leaving group, which is going to be faster, amide or acid chloride? Acid chloride, so slower and faster. Now, what about resonance? You might say, why the heck are we considering resonance? Resonance is like money. If the molecule doesn't have it, it wants to get it. Why should that matter in the step where the leaving group is ejected? Well, imagine the nucleophile that came in has a lone pair on it. So when this tetrahedral intermediate ejects the leaving group and restores the pi bond, that means resonance occurs again. So how much resonance is restored potentially is an issue. But in this case, since the nucleophile is the same, the resonance that's restored is the same. In both cases, it's a carbonyl having an oxygen next door. So in this case, not going to matter. In some cases, it will. Imagine you have the same functional group but reacting with two different nucleophiles. The resonance that you get at the end in this step may matter. Here, it's equal. Again, because the nucleophile is the same. So the second step summary, these factors we've looked at, the resonance equal in this particular case, but the leaving group is the key. Acid chloride is faster. All right, what is our conclusion overall then? Well, it turns out, right here it is. These things are synergistic. The resonance, the nucleophilic attack on the carbonyl, the key factor was the resonance. The acid chloride has less resonance to lose, so that step is faster in the acid chloride case. In the second step, the acid chloride has the better leaving group, so so the leaving group being ejected will be faster. Those two work together, and they agree with the observation that amide reactions with water are slower than acid chloride reactions with water. Now, in general, if you extend this and look at a whole bunch of different nucleophiles and carbonyl-containing functional groups, it turns out that these factors are generally synergistic. In other words, you really don't have to go through this kind of detailed analysis every time. Generally speaking, better leaving groups have poorer resonance with the carbonyl. That's particularly an atomic radius and electronegativity issue. And so often you get acid chlorides, for example, reacting faster than amides. So you can go one step further with this and look at all of the carbonyl containing functional groups that might undergo substitution. And we can make a general ranking. So here we have all the carbonyl containing functional groups that undergo substitution. And as it turns out, acid chlorides, anhydrides, and thioesters together as a group are faster than esters. And that's generally because there is less resonance in better leaving group. Esters generally react faster than amides. Now, esters and amides they're both second row X elements here, doing resonance with the carbonyl. So it's good resonance in both cases. But the amide case is slower because, number one, it has a poorer leaving group, and number two, amide resonance, nitrogen with the carbonyl, is a little bit better, a little bit more stabilizing than oxygen resonance with the carbonyl. Anybody know why that is? Why should nitrogen be more inclined to share its electrons than oxygen? Electronegativity, right? Resonance is still electron sharing, and the more electronegative you are, the less inclined you are to share your electrons. So nitrogen, being less electronegative than oxygen, shares better. The resonance is a little bit stronger. Now, the very last in this group, and I'm going to put a couple of arrows here, are the carboxylates. Remember, the carboxylate is the conjugate base of the carboxylic acid. That's this thing. These things are pretty resistant to nucleophilic attack. As a matter of fact, so resistant to nucleophilic attack that we will, in all our discussion of carbonyl reactions, we will only find one nucleophile that will be powerful enough to attack this thing. This thing resists all other nucleophilic attack. Why is that? Imagine you're a nucleophile coming along, perhaps you have a lone pair, and you're looking at that carbonyl and saying, hey, I think I'd like to attack that carbonyl. Why would you take one look at that carbonyl and go, I ain't going there? Resonance, right. This has wonderful resonance. This has the best resonance of all of the carbonyl-containing functional groups that we're talking about because the two contributors are degenerate, equal energy. All the other cases have resonance, but it's just not as good because in the other cases there's one really good contributor and other less important contributors. Here, two really good contributors. So that's one reason. Lots of resonance to disrupt. What's another reason that a nucleophile takes one look at a carboxylate and says, no, not today? I'm sorry? Repulsion. What kind of repulsion? Yeah, electron repulsion. Many times this nucleophile is negatively charged. The carboxylate is negatively charged. When's the last time that we've had two things which are electron excess to react with each other? Things which are electron rich generally avoid other things which are electron rich. So this is a combination of the resistance of this to nucleophilic attack is a combination of very good resonance stabilization and this negative charge repulsion issue. All right, so what do I want to do here now? Now what I want to do is take what we've learned and apply it to, in our next couple of minutes, a sample problem. What we're going to do in this sample problem is take this reaction, which is an ester plus base to make a carboxylate and methanol. We're going to work out the mechanism, we're going to rewrite it and make it a little bit faster, and then we're going to talk a little bit about equilibrium. So let's do that. Let's talk about, first let's do the mechanism. We have an ester, we have hydroxide, and we have methanol. I won't include the Na because, as we've seen many times up to this point, metal cations, for the most part, don't participate in a meaningful way. So the product is a carboxylate. What do we do? Well, we have a carbonyl. Carbonyls do three things. What are the three fates of a carbonyl? Every time you see a carbonyl in a reaction mechanism, regardless of where it comes from, you might think about resonance first if you'd like, but in terms of how it behaves in the mechanism, three choices. And actually, it's two choices, because one of the fates I've said we're not going to worry about for the moment. We'll get to that later. So there's only two things what the carbonyl is going to do. It's going to react at the top or it's going to react at the bottom. Right? Reacting with the top, accept an electrophile, usually a proton. There's a restriction on that. Go back and look at the three fates of the carbonyl. What's the restriction? If we're going to react with a proton at oxygen, what's the restriction? Strong acid. You have to have things like sulfuric acid. Not water. Not methanol. Methanol is a horrible acid. And hydroxide, I don't even want to go there. So that's kind of out. What are we left with? Let's see. We're not going to make an enolate. We're not going to put a proton on the oxygen. So what's left over? What did I say? Does every single carbonyl containing reaction mechanism include at some point? Nucleophilic attack on the carbonyl. So some nucleophile is going to do this. Okay, here are our nucleophile choices, hydroxide or methanol. What's going to attack it? Hydroxide, because hydroxide is the better nucleophile. It's got the formal negative charge. So here's hydroxide. Best nucleophile present attacking the carbonyl. This new beast that I've drawn here is called a tetrahedral. Very good. Remember, the carbon goes from sp2 to sp3 to tetrahedral. A tetrahedral with a negative charge on the oxygen, when it wakes up in the morning and it looks at its to-do list, it doesn't even turn off the alarm clock because turn off the alarm clock is not on its to-do list. It only has two things. It doesn't even go to sleep because go to sleep is not on its to-do list. It only does two things. One of them is try to eject the leaving group, and the other one is go back and look at, remember last time I put in the red box the generic mechanism that said we can do addition or substitution? Right? So accept a proton is the other possibility, eject a leaving group or accept a proton. Which do we try to do first? Right? Imagine, let's see if this metaphor works. Imagine this thing, this tetrahedral intermediate, it has Facebook and it has Twitter. That's all it has. Nothing. It doesn't have to study for a 14D exam. It doesn't have to go to MapQuest and figure out how to get to Burbank. It doesn't have to read War and Peace for class. Facebook and Twitter is all it has. It doesn't even sit in the coffee shop and do it because it doesn't need coffee. Now it has a choice. Which one can I do first, Facebook or Twitter? Now, that's where the metaphor falls apart, of course. But in the case of the tetrahedral intermediate with a negative charge, it does the intramolecular thing first. What's the intramolecular thing? Tries to eject the leaving group. All right, so there is the reforming of the carbonyl. There are three leaving group possibilities here. We have a methyl group. And by the way, this may sound like I'm repeating something over again that I've repeated several times because I've said it several times again over. I mean, it would be repetitious to say that I'm being repetitious, but I am being repetitious because there's a point in me being repetitious. These patterns that we're talking about, what does a tetrahedral intermediate do? What does a carbonyl do? You're going to do them time and time and time again when you do carbonyls. Hopefully at some point you'll be doing them in your sleep. Not during the exam. That's not a good time to do them in your sleep. All right, so here we're going to try to reform the pi bond, kick out a leaving group. What are our leaving group choices? Methyl group. Never, ever, never, ever do methyl groups CH3 minuses leave. OCH3 minus. Can that leave? Remember, negatively charged tetrahedral intermediate can eject OCH3 minus. Now, obviously that moves the reaction forward, but we should consider the other case. What about hydroxide? Could that leave? It's pretty much the same leaving group ability as OCH3 minus. So this can leave as well, but that's not productive. It's happening, but it's not productive. OH is going in, out, in, out, in, out. Eventually, OCH3 gets kicked out and it moves forward. But are we done yet? We know what the product of our reaction is. Is this the product of the reaction? No. What's the name of this functional group? It's a carboxylic acid. Why is it called a carboxylic acid? It has nothing to do with the 60s and what illegal substances it took. If that was the case, we'd call it a carboxylic LSD. It's called a carboxylic acid because it likes to give away its proton. And that's what we need to do to get up here. So we need to deprotonate it with something, which we deprotonated with. We use the strongest base that's present. What's the strongest base that's present? You could use hydroxide, or you could also use the methoxide you just kicked out. If they're equal basicity, doesn't really matter. We'll use hydroxide today. So there is our deprotonation that takes me up there. Now you might say, why are we doing that? That's not a substitution step. It's because you can't avoid this. Strong base, strongish. I mean, it's not like sulfuric acid, but it's not like methane either. It's a stronger acid, so this can't be avoided. The equilibrium lies very much on the carboxylate side. And by the way, why do you think the equilibrium lies so much on the carboxylate side instead of the carboxylic acid? Hold that thought because we're going to talk about that next time. But we're going to do something else first before we quit. Something related to this part 2 of our question, which says, rewrite it to make it faster. Now, this is a carbonyl substitution mechanism, so we can target this step, or we can target this step in terms of making it faster, because neither one of those is rate determining. They both have a significant impact on the rate. So somebody give me a suggestion, something I can do to this first step to make the reaction faster. Change the leaving group? Okay, what should I change the leaving group to? We're going to keep the nucleophile the same. You want to change the leaving group to iodide? Oh, good choice. We'll get the same product. Now, your textbook, even my textbook, doesn't talk about acid iodides. And that is because these guys are so susceptible to nucleophilic attack that bits of water vapor in the air are enough to do this. They also like to do free radical reactions where this bond breaks by a radical process. So while they're in paper are wonderful things, we don't use them in the lab. You're welcome to use them on paper all you want. We just don't use them in the lab. Let's do something. So there's other things you can do, by the way, to make this faster. We did a better leaving group. You could make for a better nucleophile. Although it's kind of hard to think of better nucleophile and hydroxide under these circumstances. We could make for less steric hindrance by converting this methyl to a hydrogen. All right? Let's target the second step in the mechanism. What can I do to make this step faster? Somebody give a suggestion. Hint, we already have the answer. What should we do? Change the leaving group, right? Now, up here, to be fair, in this step, changing the leaving group doesn't make it faster because it's a better leaving group. Here, it makes it faster because there's poor resonance. But down here, if you make a better leaving group, it's faster because, well, I minus is a better leaving group than methoxide. So sometimes changing the leaving group will change multiple things. All right, so here's what I'm going to leave you to think about for Monday. The last question up here is, does this equilibrium lie to the right or to the left? Now, that's an important issue because unlike a lot of the other reactions we've talked about up to this point, carbonyl reactions are very strongly influenced by the position of the equilibrium, so we need to understand that. So that's where we're going to pick up next time. See you Monday.